So first, I usually review major points like I did in online exam review session. So on the exam, we're going to cover what? Everything from capacitors, chapter, basically beginning of chapter 26, and all the way to RC circuit, right? All right, and after that, we move to the magnetism, but magnetism is not going to be on the exam. So first, we introduced capacitors, and definition of capacitance was very simple. If you have two electrodes, one is positively charged, one is negatively charged, of course, between them, there will be potential difference. And naturally, definition of capacitance is just the ratio of charge versus potential difference. Then we applied this definition of capacitance for a parallel plate capacitor, and we got this formula, right? So the major feature of this formula, it doesn't depend on charge or potential difference, so nothing like that, only on material between the capacitor, between the plates of the capacitor, which is in this case vacuum, area, and distance, basically geometry. Then we increased complexity, we added capacitors, several, and first we discussed the method of an equivalent capacitance, right? So the idea is you replace a bunch of your capacitors connected either in series or in parallel with a single equivalent capacitor, and when you do that, the rest of the circuit must work in exactly the same way. You do not want to disturb the rest of the circuit. And so we derived the formulas, which can be used to find equivalent capacitance, and also very important piece of physics, charge in the equivalent capacitor equals to the charges in capacitors connected in series. So this is series case, and this is basically major feature of things, capacitors connected in series. Then similar for capacitors connected in parallel, formula for the which can be used to calculate equivalent capacitance. In this case, it's much easier, my favorite. And then, important piece of physics, potential difference across capacitors. Across equivalent capacitor equals to the potential differences across capacitors connected in parallel. Right? Okay, you had your take-home, no, in-class quiz about this, so we're not going to practice that. So I will probably practice equivalent resistance. But anyway, so this might be on the exam. Then after that, we introduce current and quantities related to the current. So first current, how did we define it? If you take a cross-section, any cross-section of the wire, and sit there and count amount or measure amount of charge crossing that cross-section, and let's say you measured it over a short, infinitesimally short period of time dt. So if you take a ratio, dq charge, which passed your cross-section divided by dt, that's basically, by definition, the electric current. Right, then we introduce Ohm's law. Basically, we introduce the idea of resistance, So let's say you have some, I don't know, piece of wire or piece of a resistor, and let's say you apply potential difference delta V. Of course, as a result, current will flow, and so if you take a ratio of delta V versus I, that ratio will be exactly the same all the time within experimental error. So we call it resistance. That's what a resistance by definition, and of course, that is basically Ohm's law. Then we dived inside of the resistor in order to see on what that quantity might depend. So if you have some cylindrical conductor, cylindrical resistor, right, of length L, cross-sectional area A, and it can be made out of some material, then we found that resistance can be calculated by taking resistivity, it's tabulated numbers, right, times length of the resistor and divided by the cross-sectional of the resistor. Lots of similarities between this formula and that formula. They both depends on the geometry and the material, basically. Again, the resistivity property of the material, and that is geometry of the resistor. Then, naturally, definition of current, density. You take current divided by the cross-sectional area. That's the current density. Then, since we don't use electric energy in our life most of the time we convert it into something else, then of course, logical question, how much of energy per unit time we convert into something else, into heat, into light, into audio signal. So we introduce electric power, which can be calculated as current times the potential difference across device, which converts your electric form of energy into something else, or square of the current times the resistance, or square of the potential difference across element divided by the resistance. Okay, we just recently practiced that. Then we also introduce equivalent method of an equivalent resistance, similar to method of an equivalent capacitance. So in this case, two resistors connected in series, right? All right, and so again, we replace them with one equivalent resistor, and the value of which can be found by just adding R1 and R2 in this case of a series, resistors connected in series. And what is very important piece of physics, current in the equivalent resistor must be equal to the currents in resistors connected in series. Again, we need that when we analyze circuits. Then, in case of resistors connected in parallel, right, this is the formula which can be used, reciprocals, 1 over R, 1 over R, 1 over R, and potential difference across an equivalent resistor equals to the potential differences across resistors connected in parallel. Right? Again, we practiced that, but we will look at one more problem. After that, since this method is quite limited in terms of applicability, you can use it only if resistors connected either in series or in parallel. But plenty of cases when they are not connected like this. So in this case, we introduce Kirchhoff rules, which are universal. So junction rule, the total amount of current entering junction point equals to the total amount of current leaving. If you take any loop and start walking around that loop, counting all the potential differences across each element, when you get back to the starting point, you must end up with 0. Okay, so, and after that, we went to the last section, which we just finished discussing a couple of classes ago, RC circuit. First example where current is the function of time. Actually, all quantities are functions of time. Currents, charges, potential differences, all are functions of time. And we discuss two situations. Charging case, discharging. So here, capacitor originally is empty, and then we charged it using, more people, more fun. It's like old commercial, more flags, more fun. I don't know if they still use that commercial. 6 flags, you remember. Okay, so EMF, potential difference across the battery, resistor, and capacitor, right? So charge Q, it's a charge inside of the capacitor. So we derived formula, which can, not formula, function. Formula doesn't sound good. Function which describes how charge in the capacitor changes with time. So, and this is the plot. Again, we used it in our recitation, in our lectures. And then current can be found using this function, right? Exponential decay. So at the initial moment of time when you close the switch and start charging capacitor, it's maximum, and then it decays. And when the capacitor is full, current stops flowing, right? Then RC time constant, actually I didn't write over here. I wrote over here on the RC time constant, but it's exactly the same for both circuits, right? R times C. And discharging situation, circuit slightly simpler. Now we don't have battery. We have a first at the initial moment of time capacitor, which is full, and then it gets discharged through the resistor. Again, everything is a function of time. Q, current, and that is the function which describes charge, behavior of the charge in time, and this is behavior of the current in time. The behavior of the current exactly the same in the charging case and discharging case. And plus, we watched the movie about this situation, right? Okay, so that's the scope, right? And in my opinion, exam number 2 probably one of the easiest out of three exams. Usually students do reasonably well with these simple circuits, especially guys from EE department. For you, this should be really simple. Okay, girls, we just came. At any moment, you can ask any questions. If you feel like you need to go somewhere, go, or if you want to come back, yeah, it's our free time. So no one forces us to do that. So I prepared maybe like 6 or 7 problems. So it will take us at least 2.5 hours. So first about a capacitor. Let's play with this. Something like similar to this problem we had in our recitation class, but I slightly changed it. And again, we're just reviewing it. We're not trying to introduce something new. So problem number 1. So let's say we have a PP capacitor, parallel plate capacitor, right? And parameters of that capacitor, I will draw the picture in a second. Let's say area is basically area of plates. 25 centimeters squared. Then a distance, you know what? Distance I will write when I write down that it's a part A and B. Right. Then there is a battery, and potential difference across the battery is 12 volts. Okay, and so now in part A, so the spacing distance between the plates is what? I don't remember, 2 millimeters. Okay, so let me draw the picture, very simple picture. So let's say this is my capacitor. Right, so that is my battery. So delta V. Then distance D1, and that is the cross-sectional area. And the question is, in part A, we need to find the amount of charge. We need to find Q1 in the capacitor. Right? It looks like I gave you everything. Yeah. So, first of all, again, I want to remind you guys, I have told you many times in my recitation classes and in the lecture, whenever you work with a capacitor, you need to think about 3 parameters, C, Q, delta V. So let's look at all of those 3 parameters. Right? So let's start with delta V. Delta V across the capacitor equals to the potential difference, of course, across the battery, right? We discussed that, right, at the very beginning. Equals to delta V, and of course equals to 12 volts, right? I don't want to repeat that one more time. So potential difference. Then, what about capacitance? Capacitance. Can we find capacitance? Geometry is given, essentially, right? Geometry is given. Area is given. Of course, we need to convert into normal units, correct units. Then distance is also given, and the vacuum between the plates. So we can calculate capacitance easily, right? So it will be right epsilon naught A divided by D1. And I guess I will write down the numbers. Yeah. I don't like plugging numbers, but at this point I feel like probably I need to. Times 10 to the power of minus 12. And okay, I will skip units. But I will, no, you know what? I need to write units. Because we have weird units for area and for the distance, so I need to show that we will eventually cancel and get the correct units at the end. So newtons times meter squared. And so area, 25. And centimeters to the power of 2. So we need to get rid of those centimeters. So in order to do that, we need to write 1 centimeter, it's 10 to the power of minus 2 meters. And then again, the same ratio, 1 centimeters, it's a 10 to the power of minus 2 meters, right? Okay. Probably I should have converted it somewhere separately. Right. Correct? Don't square 25. 25, we're just converting units. So 2 centimeters times centimeters. So I get rid of 1 centimeter, and then I'm trying to get rid of the 2nd centimeter. And so downstairs we have D. D1. It's in millimeters, so it's 2 times 10 to the power of minus 3 meters. Okay, so of course I'm not going to actually use calculator. I will write down the answer immediately. So that will be 11.063. So I keep more sig figs because it's not the final result. Negative 12, basically picofarad. Right, so found capacitance. So CQ delta V, we analyze delta V, we analyze C, so now we can answer the final question. Finally, we can answer the question Q1. Q1, again, from the definition of capacitance, Q, it will be C times delta V. All right, C1 times delta V. Okay, so now, of course, we can plug numbers. Times 12 volts. And of course, the answer will be 1.33 times 10 to the power of minus 10 units of coulomb. Great. Okay, so that's basically part A, which is straightforward. It's basically plugging numbers in the correct order in the correct formulas, two formulas. So now part B. So now let's still keep the capacitor connected to the battery, but let's reduce the spacing by a factor of 2. Right. So now reduce distance d. So let's say d2 will be equal to d1 divided by 2, which is where is my value of 2 millimeters, so 1 millimeter. So it will be 1 millimeter. And the same question, now let's find the value of now Q2. Find the amount of charge in this case. The amount of charge in this case. So let me quickly redraw the picture. So now, of course, distance will be smaller. Battery stays the same. So this is, let's say, D1. Oh, no, D2 now. Area still the same. Right? Still vacuum between the plates, so we didn't change anything except for the distance. And delta V still the same, connected to the same battery. And again, so it's just a different capacitor. So again, we need to analyze 3 parameters, CQ, delta V. Again, delta V2 will be equal to the same potential difference across a battery. You remember in the lecture and then in the recitation classes, we discussed this situation. So if a battery is connected, if a capacitor is connected to the battery, then it doesn't matter what you do with this distance between the plates, potential difference is going to stay the same, right? But let's say if we disconnect the battery, which parameter would stay the same? Let's say we charged the capacitor, and then for part B, let's say we disconnect the battery and then reduce the distance between the plates. Which parameter would stay the same? You say something? Of course, charge. And you remember the example which I gave, at least in my recitation class. It's an analogy similar like to the ocean liner. So if you fill it with people, let's say somewhere by the shore, let's say 1,000 people, it's like charging a capacitor. And then ocean liner goes into the ocean, right? And then it doesn't matter if you count number of people after 1 day of trip or 2 days of trip, number of people will stay the same because they basically trap inside of the ship. And that's what happens here. So here, first capacitor is connected to the battery. So you load capacitor with people, with passengers, right? And then once if you disconnect the battery, all those people, all those electrons are trapped inside of this capacitor. And then doesn't matter what you do with the plates, they're there, they're stuck. But again, it's a case if you disconnect the battery. In this problem, we do not disconnect the battery, but you need to remember, if capacitor is connected, potential difference stays the same. If you disconnect the battery, charge in the capacitor stays the same. Again, we had those questions in the lecture. Okay, so now, then second, capacitance. What can you say about capacitance? Does it change? We changed geometry. So capacitance must change. So C2 equals to epsilon naught A divided by D2. And now I don't want to plug in numbers. I did it once, Enough. I don't like plugging numbers, right? Especially those numbers. So epsilon naught A divided by what? D1 divided by 2. I want to recycle my previous numbers, right? So these 2 will go into the numerator, so it will be 2 times epsilon naught A divided by D1. And this construction in the parentheses, it's a C1, right? It's our capacitance in part A, so I can recycle it. So 2 times C1. And even now, I still don't want to calculate it. And this number, because it's not the final result which we want to get. Okay, and charge. Now let's find Q2. And again, according to the, from the definition of capacitance, so it's a C2 times delta V. Delta V, again, the same. And so again, I will use our 2 times C1 and delta V. And C1 times delta V, what is that? C1 times delta V, it's a charge in the first part, in part A, you see it's a Q1. Again, if you calculate one more time, it's not bad, right? It's absolutely correct, but I want to recycle it, recycle results. Now recycling is popular. All right. So 2 times Q1, right? And actually, you know what? I forgot. It's not just we need to find the amount of charge in the second case, right? Actually, now you can calculate. So Q1 times 2, so it will be 2.66 times 10 to the power of minus 10. It asks for the extra charge that this capacitor is going to get. Actually, where does this charge, extra charge, comes from? What's the source of this charge? Look, in first case, we had Q1. In case B, we have 2 Q1, so extra charge Q1. Where does that charge come from? Very, very simple question. There's only one place. From the battery. We just drained the battery, right? Yeah, of course, very simple. It's like if your ocean liner stands by the shore, right? So people can go inside of the ship or go back right on. So yeah, capacitor, I mean not capacitor, battery is the source of an electron. So in this case, let me write, so since the question is about extra charge, so basically it's a delta Q, which is equal to Q2 minus Q1. Right? So that's the amount of charge that battery additionally provided. So 2Q1 minus Q1. So it will be Q1. So which is, I calculated in part of A. So the follow-up question, what if I didn't reduce spacing between the plates? But what if I increase the spacing between the plates? What would happen to the charge? Molly. What would happen to the charge if we increase the spacing? The charge would go down. And then the question for you again. If we increase the spacing, let's say, imagine, she said this charge Q2 would go down. It will be smaller than Q1. The question is, where does that charge go? In our case, right, so battery provided charge, extra charge. But if charge went down or goes down, where does that charge go? There are only two spots, either capacitor or the battery, right? It goes back to the battery. Basically, what you do, you recharge your battery. So, of course, you will do some work. You will pull your plates apart. You will increase the spacing. And because of that work, you will push electrons back into the battery. So you will recharge it, right? First, you drain it, and then you can recharge it. Okay, yeah, it's very simple. There are only two objects, capacitor and battery. Great. So it's not that bad, right? Again, it's the goal is just to refresh. Okay, I will have to erase it because I don't want to move the camera around. I can write up to this point, but yeah. Say it again. Q1 equals to Q2. On which basis can you make that statement? No, here I wrote that delta Q equals to Q1. It's just the amount of extra charge that came from the battery equals to the amount of the original charge which was in the battery, which was in the capacitor, So Q1 equals to Q2. It's a very bold statement, right? You'll have to prove it, right? Unless I misunderstood you. This? No. That is true for if you use an equivalent capacitance, right? And that is true if you introduce equivalent capacitance instead of two capacitors connected in series, right? Now those are you cannot apply law. I don't know about business to the law. I mean to control something which is not connected to business, right? So those are apples and oranges, basically, right? Yeah. Okay, so then I can probably erase, and the next problem, okay, the next will be also very simple, and it's kind of difficult to find something not simple about Ohm's law. Plus, you all, probably it's the most favorite law of students in physics too. Usually do really well. Okay, so now let me erase this. And then there will be more challenging problems. So, number 2. So what we have here, cylindrical wire, very long, 46 meters. Yeah, it's almost like a spool of wire, most likely. Okay, so we have cylindrical wire. And let me write parameters describing that wire. Radius. I think I used R small. Yeah, R small. Radius is 2 millimeters. Okay, let me convert immediately to meters. It will be 2 times 10 to the power of minus 3 meters. Then, length. Length is 46 meters. And you know what? I probably will start drawing picture immediately because then it's easier to imagine what are we talking about. So that's our wire. Right. Length is L, 46 meters. Then this is then 2R. Basically diameter R is given, but then of course that is 2R. And this whole thing, this wire is, I think it's, yeah, and then it is connected to a battery. And potential difference of that battery, I think, is given 3.7. Right. So I use just delta V. Okay, delta V. Right. So delta V equals 3.7 volts. And we also, let's say we measured current. Current through the wire is I. Right. And the value of that current, I guess I can move further, 2.5 amps. Let me check. It looks like, yeah, I gave you everything. Yeah. Let's say we want to calculate, actually, we want to find out which material is used to fabricate, to make this wire. I know you found a piece of wire somewhere in the corner of the lab, right? You took some battery, right, connected, measured the current in order to find out resistivity, and then you can look up the in the table reference books, and approximately you can. I've done it once or twice in the lab when I wanted to find something. Right. Okay. So we need to find raw resistivity. As I said, it's kind of practical situation which you can experience if you start working somewhere in the lab or the company. Right. Yeah. So resistivity. It's only there's resistivity only in one place, right? It's here. Right, you remember we look inside of the resistance, so it's a resistivity L times L divided by A. Right? So I can write R equals rho L divided by A. So that's where our global unknown is. So let's see. L is given. Cross-sectional area, piece of cake, we can calculate. It's cylindrical wire, right? So we can calculate, right, pi r squared, right? You look so confused, right? Yeah. Okay. Right. So it means that we need to somehow find this resistance. And the resistance should be easily found because delta V is given, and we actually also measured the value of the current. Ohm's law will allow us to find R, and then once you know R, you can calculate rho. So as I told you, this again, a reasonably simple problem. And R can be found, of course, from the Ohm's law. So delta V divided by current. So it's a very, very simple. So if we combine them, of course, basically I plug instead of R that. So it will be delta V divided by I equals to rho L divided by A. Actually, you know what? A, we can calculate, right, area of the circle, pi r squared, right? Again, guys, if you're not confident, usually in the formula sheet, I wrote all the formulas, like area of the sphere, volume of the sphere, radius, area of the circle, because every exam I see really, really silly mistakes when students just use the wrong formulas, right? It's really kind of not necessary mistakes. So rho L divided by pi r small squared, right? Okay, so now, of course, we just need to look at these two sides and solve it for rho. So rho equals pi r squared goes up here, pi r squared times delta V. Again, I move this side to there. And this L will go in the denominator next to I. Li. L times I. So now we just need to plug numbers. And yeah, that's correct. Or maybe I will plug 3.14. Then R, what is R? 2. 2 times 10 to the power of minus 3 meters to the power of 2, right? R squared. Delta V, it's a 4.7. 4? No, 3.7. 3.7 volts, and divided by L, 46 meters. And current, 2.5. Okay. So of course I will use my notes. 4 times 10 to the power of minus 7. 4 times 10 to the power of minus 7 units, ohms times meters, right? And then you just open the reference book, right? And you can see which material most likely is going to be. Okay, so that's very simple. And you know what? Before we go to the next problem, Just quickly, conceptual thing. Again, as I said, if at any moment something is not clear, say something. Very simple. Let's say we have this wire of this shape. You remember most likely, right? So let's say we have section 1 and section 2, and let's say current I flows through this wire made of the same material. What can you say about current in the first section and current in the second section of this wire? What do you think? What can you say about this current in the first piece of wire and current in the second piece of wire? Which one is larger, or what can you say about these two currents? Yeah, say it. The same, right? Again, usually at this point, students remember that. Okay, so good, it looks like. But what about current density? Yeah. With current density, of course, we have to be careful with it. Sometimes students made mistakes over there. So J1 equals to, of course, I1 divided by, okay, I is the same basically, right? I can skip subscript, right? Divided by A1. And J2, it's I divided by A2. And since A1 is smaller and it is in the denominator, so it means that J1 is going to be larger. Current density is going to be larger. Okay, good. Just wanted to remind you about that. And of course, usually most of the time, you guys at this point already aware of this. Okay, you know what? I thought about skipping this problem, but no, let's discuss it. See your thumb, so I can erase it. Right. Again, related to current, Ohm's law. This mic is more sensitive. In only 150, it doesn't pick up all these noises of my clothes and so on. So, problem 3. Actually, I think this problem from what I gave once on one of the exams a few years ago. Again, a reasonably simple circuit. Let me draw it, and then I will write down what is given. So we have a battery, and then we have 3 resistors. First, second, and then the third one. So they're connected like this. So now let me label them. R, then 2R, 2R, and this is EMF. Of course, this is positive electrode. Right? And on top of this, first let me write down the value of this current. I mean, the value of R is given. So R equals to 12 ohm. And on top of that, current is given. Current, which goes, total current, which goes from the battery. So basically, the total amount of current taking from the battery is given. So that current I. So it's pretty much the value of the current up to this junction point. After the junction point, of course, story will be different, right? So that current is given. Okay, let me restart the camera. Because this camera is reasonably old, like 6 years old, and it can only make certain file of a certain size. So after that, it just shuts down. So after like 50, usually after 18 minutes, I need to restart it. So I set up the alarms for each time. Okay, so the value of the current is given, and that is half of the amp, 0.5 amps. Right, so we need to find the EMF of this battery. So we need to find electromotive force of the battery. So first of all, we need to understand which method can be used, because now you see we have a bunch of resistors, right? And first question, can we use method of an equivalent resistance? You look so confused. Look, what can you say about this resistor and this resistor? How are they connected? Are they connected in series or in parallel? Parallel? Why are you not confident? You should say, parallel, right? Analysis is very simple. You remember what's so special about elements connected in parallel? Potential differences are the same. Potential differences must be the same. So look, these points on this side of this resistor and the point above this resistor, they belong to this piece of metal, the same potential. Then this point on this side of this resistor and points below this resistor, they belong to this piece of metal, piece of wire. So they must be also the same potential. And so that means, let's say 5 minus 3 give us 2 volts. 5 minus 3 again give us, for example, 2 volts. Right? So potential differences are the same. So they're connected in parallel. So these two elements in parallel. So basically what I'm trying to do, I want to simplify the circuit to the simplest possible with one equivalent resistor. And since values of resistors are given, so I should be able to calculate R equivalent. And then at the end, we will have battery and across a single resistor. And current, you remember, once you make all these replacements, battery works in exactly the same way, and this current must stay the same. So in equivalent circuit, our current is going to be still the same, right? So you remember that major feature, one of the major features of when you apply method of an equivalent resistance. So we will know current, we will know resistance, Ohm's law, and we will be able to calculate potential difference across the battery, which drives that current through that equivalent resistance. Right. Okay, so that's the sort of strategy of the solution. And now let's actually simplify it first. So these two guys are connected, as you told me, in parallel. Right. And of course, we can redraw this circuit very quickly. Okay. This stays the same, and now we will have, okay, this is R. And which way I label it? I don't remember. R1. Okay, why not? Equivalent resistor R1. And the value of that R1 in parallel, we need to use the reciprocals. My least favorite. All right, so 1 over R1 equals to 1 over R, 2R and 2R. Right, so 1 over 2R plus 1 over 2R. I'm afraid that I will break my antenna at some point. So of course, denominator is the same, so it will be 2 divided by 2R. So it's a 1 over R. So equivalent resistance R1 equals to R. So R1 equals to R. Okay, so that's some preliminary result, not the final result, of course. And so now, and again, once you made this replacement, the rest of the circuit, in this case battery, must work still in the same way. So the same EMF and the same current. The same current is taken from the battery. So, and of course, the final step, now these two resistors obviously in series, right? I'm not even asking you, right? So, because there's no any junction point between them, so current must be the same, and that's basically a major feature of things connected, resistors connected in series. So, in series. And, okay, the final circuit. Battery final are equivalent. And again, battery still the same EMF and the same current. And our equivalent, it's a series, it's trivial. So our equivalent equals to R plus R1, R plus R. So it's R plus R equals to 2 times R. So that's the value of an equivalent resistance. And trivial circuit, direct application of Ohm's law will allow us to find. So EMF equals to I times R equivalent. R equivalent, it's a 2R. So I times 2 times R. Current is given, R is given, problem is solved. So let me write underneath. 0.5 amps times 2 times 12 ohms. 0.521, 12 volts. 12 volts. Okay. Again, the major thing, resistors in parallel potential differences are the same. Resistors in series currents are the same. So basically, that's the sort of like a test that you have to check to convince yourself that they're connected in series or in parallel. Great. So the next one, somewhat lengthier, right? And in the past, students struggled with this problem where we have to apply equivalent method of an equivalent resistance. In a similar way, like sometimes, quite often students struggled with the method of an equivalent capacitance, but this time I pushed you, I gave you the quiz, take-home, no, in-class quiz. I told you that will be on a quiz, so prep yourself, realize how that method works. So I hope it will work for you. But anyway, so let's get through that somewhat lengthy problem. Again, just to review. Okay, and then there will be Kirchhoff rules. Okay. Now, problem number 4. After 2 years of running virtual exam review sessions, kind of, I got used to working in my studio at home. Okay, anyway, so let's analyze a more complicated circuit. So it's a problem number 4, and we need to analyze the circuit. Analyze, this circuit. And again, what does it mean analyzing in this case? I will write down maybe in a few minutes. First of all, I need to draw circuit. And you remember how I organized these problems, right? So I will write first, draw circuits somewhere in the middle, and then I will write on both sides around that circuit, right? So you remember that. All right, so I will leave some space here. And so I will start drawing circuit here. So first, battery, then first resistor, then, you know what, I need to step slightly away more. Then the second resistor, then junction point, and there are 2 more resistors connected like this and connected like that. Yeah. So now let's label all these resistors. So delta V, potential difference of the battery. I will probably write it here. So delta V is 24 volts. Then Okay, I will start from the bottom, R1, R2. So this is R1, R2, R3, and R. I realize. No, everything is good. Everything is good. I remember, I think I used this problem at some point in the previous exam review sessions. And I remember I realized that one R in terms of order is missing. So I have R1, R2, R3, and then R5. And only now I noticed that again, like after 2 years or so, that kind of out of order. But again, it's not a crime. So R4 is missing. And I don't want to change because then I cannot, it will be more difficult to compare with my notes, right? And sometimes you need it. Not very likely that I will need, but okay, R4 is missing. Right. So now values of this are, you know what, I will write it here. R1, 6 ohms, R2, 12 ohms, R3, 4, and R5, 2 ohms. Okay, let me write. No R4. And of course, we need to analyze. Again, what does it mean analyzing? Analyzing, since we have a bunch of resistors. Again, if you talk about the resistor, you need to, in order to know everything about the resistor, you need to know resistance, potential difference across the resistor, and current through each of these resistors. Resistances are given, so we just need to find voltage drops across each resistors and currents. So effectively, we need to find I1, 2, 3, 4 is missing, so it's a 5. And delta V's, right? So the same. So delta V 1, 2, 3, and 5. So these are our unknowns, tons of unknowns. And so procedure is well known, right? So we just need to refresh it. So let's start searching for the resistors connected either in series or in parallel, right? And the first one, R1 and R2 in parallel, right? Again, because potential differences exactly the same. Not just because they are graphically parallel to each other, although they're parallel graphically as well. Right? So these guys are parallel to each other. So parallel. But anything else at the same time, maybe we can take care of something else. R3 and R5 in series, so we can make 2 steps, okay, 2 manipulations in 1 step. I'm trying to be more efficient from a management point of view. Right, so in series. Right. Okay, so as a result, we can replace them and redraw the circuit. Let me redraw the circuit, and of course, the battery must work still in exactly the same way. So let me draw the battery, then resistor, and then another resistor. Right, so that will be the first equivalent circuit, not the final one. And again, as we discussed, so delta V must be still the same. All right. If current I is taking from this circuit, of course, exactly the same current must be taking in this equivalent circuit I. Right. And resistors, equivalent first R35, second R1, 2. So let's calculate those resistors, which is trivial. So R35 in series. In series, we just need to add their values. Right? So the easiest possible situation. So it's R3 plus R5. And those are 5, 2, 3, 4, 6 ohms. Wow, time flies. So I'm interested. You can, okay, if problem doesn't say that you have to apply a certain method, then you can do anything you want. You can even apply some voodoo method, right? As long as you can get the correct answer and you can justify it, right? Yeah. It would be unfair from our side, unless we ask for something particular. So let's say we want to check your ability to apply this or that method, right? Yeah, you can use voltage division, but basically it's a potato. You're talking about the same thing, but using different, slightly different steps. Yeah, parallel. Now in parallel, so 1 over R12 equals to 1 over R plus 1 over R2. Right? So, of course, we can, you know what, I will just write down immediately the answer. Of course, you can bring to the common denominator, right, and calculate. So it will be 4 ohms, according to my notes. 4 ohms, yeah. So, and of course, obviously, these two guys now connected in series. Of course, I'm not asking you that question because you seems like quite comfortable. Unless circuit unless circuit is complicated, then of course you can start struggling a little bit. So in series, so we can redraw the circuit and draw the final version. So this will be R equivalent, and battery still works in exactly the same way, right? So R equivalent will be R12 plus R35. 4 plus 6. So 4 ohms plus 6 ohms, of course, that is 10 ohms. And so now the final step, we need to make a crack in this wall, right, in order to find at least something. And that something, we can find the total current taking from the battery. And that current is exactly the same as here and as there. Again, if I asked you from the very beginning, for example, what's the total amount of current taking from the battery in this circuit, it would be difficult for you to answer that question because you would have to make all these steps in your head very quickly. Right? But now we simplify it to the simplest possible, and now we're finding current is a piece of cake. Right? Awesome. So now which way I labeled this I current, just I. Okay. Delta V divided by R equivalent. Delta V, where is my delta V? 24 volts. And divided by 10 ohms. Oh, nice numbers, more or less. So 2.4 amps. Total current. So now we've managed to create this crack. Now we just need to make it bigger and to see all these unknown quantities. Let me check. Yeah, 2.4. So now we need to go back. So now I'll move to this side. So first, in the first step, this resistor replaced 2 resistors connected in series. And what's the structure of the bridge that I'm planning to write down over here? Which quantity? This equivalent resistor and these 2 resistors, which quantity is exactly the same? Yeah, where is that? Parallel, a series case, current is the same. And that's where usually students struggle. Again, I hope this semester it would be better because up to this point, I know 99% of students calculate everything properly, correctly. But on this side, it's, usually 30% of students would usually be able to complete this problem correctly, right? So that's why I decided now bombard you with take-home quizzes or in-class quizzes, right? So that to cover those gaps, right? Okay, so now currents are the same, so it means that current which we just found equals to the current I35 and current I12. So let me build it here. So I, which we just found, equals to I12 equals to I35 equals to 2.4 amps. So, you guys complained that, can you see this red color, red marker? Better when you sit in front? Yeah, okay, cool. Because at the very beginning they told me it's difficult to see a red color because not much of a contrast. Okay, maybe I will use blue next time. So, and this 2.4, as I just told you, let me show it. So it comes, of course, from the previous step. All the steps are connected. And so now, once we know current I12 and resistance R12, we found, where is it? Here. Let me frame it because. So it means that we can find potential difference. It's not what we need right now, but it will help us in the next step. In the next step, where we will actually start finding our unknowns. For now, it's just still preliminary result, but we need that preliminary result. So delta V12. Delta V12 equals to delta V. It will be R times I. So R12 times I12, and of course I12 comes from the bridge. So R12 4 times 2.4. So it will be, oh my God, 9.6, right? 9.6, yeah. Correct. Well, sometimes I doubt myself. So there's no point of laughing. Sometimes I can humiliate myself in front of everyone. It happens, right? Come on, we're all human, right? So I can make some silly mistakes. So delta V35 now, of course, in a similar way, we can find potential voltage drop across the second equivalent resistor. So delta V35. So it will be resistance 35 times current 35, which again comes from the bridge, which we just built. So it comes from here. Where's my resistance? 6 ohms. 6 times 2.4. Okay, it's getting more complicated. 6 ohms times 2.5, 2.4 amps. So 12 and 2.4, 14.4, right? Cool. I'm gaining my confidence. Right, I'm joking. Don't take me seriously. So, all right, yeah, 14.4. So now, final step, and in the final step, we will actually find all this. So inside of 3.5, let's start with 3.5. There are 2 resistors connected in series, so we will have to build 2 bridges pretty much in the same step. So first one, again, these guys in series, so we need to create a bridge out of currents. So let me write it over here, and then the second bridge will be above. Currents, so I35 equals to, it's, hold it. Yeah, current in series. So I35 equals to I3 equals to I5. And current 3.5, again, it comes actually from this. So, and 2.4. 2.4 amps. So we almost crossed the whole line. Slightly lower. In my notes, it's the next one, but okay, it doesn't matter. Order doesn't matter. So now we have current through the third resistor. We know resistance, so we can find potential difference like that again using Ohm's law. So delta V3 equals to R3 times I3. Right, again, I3 comes from the bridge. So R3, 4. All right, 4 ohms times 2.4. Again, 9.6. Yeah, 9.6 volts. And again, if you prefer just if you don't like to, I don't know, apply this method, if you just see, okay, here obviously potential differences are equals to those, right? So you can find, okay, go ahead. But of course, kind of show the steps so that we wouldn't have to guess what's the reason of this or that. So delta V5, delta V5. Again, just from educational point of view, I like this structure. It's I find it very convenient. So R5 times I5, again I5. It's from the bridge. Value of R5, 2 ohms times 2.4 amps. So it's a 4.8 volts. So we finished analyzing three resistors, 3 and 5. So we have their currents, we have potential differences, done. These two guys, right? But inside of R1, 2, we still have two resistors connected in parallel. And of course, we basically need to create another bridge. And in this case, we need to use, that bridge will be constructed out of parallel case, right? These two guys were replaced with this parallel case. So in parallel case, potential differences are the same. So that will be the last step. So delta V 1, 2. So pretty much it comes. Where is my delta V 1, 2? Here. So let me connect it. So equals to delta V1 equals to delta V2 equals to 9.6. Right. Okay, so now let's just exhaust this bridge. We can find current in current I1. So it will be delta V1 divided by R1, 9.6 volts. Sorry, divided by, where is my R1? 6 ohms. 1.6 amps. So finished R1 and finally I2. So delta V2 divided by R2, again 9.6 volts. Again, delta V2 comes from the bridge and divided by R2, 12 ohms. Wait, no way, I'm not going to calculate this. I will use my notes. 0.8. I know limitations of my brain. Of course, I can actually calculate if I stare for a few 10, 15 seconds. So, done. And again, I hope this time students do better, will do better with this problem, because usually, again, no troubles and lots of mess. This problem about equivalent resistances, you can look by yourself, right? I just provide the solution. Because we already had like 2 problems about equivalent resistances, and it looks like you guys are quite comfortable with that. You can record it for the history. All right. Speaking up, even air, basically. Wind, I mean. I need to buy, you know, that fluffy stuff, right, on top of the microphone. Yeah. I forgot the name of that full fluffy piece. Okay, I guess I can start erasing that then. Kirchhoff rule. And I need to do my duties. I bought a new camera, Blackmagic, but I don't have sort of lens which belongs to that camera. I use the lens from this camera. As a result, there are some distortions. That's right. Don't use it. Okay. I use that Blackmagic camera for streaming. So, number 5. So, Kirchhoff's rules. 5, right? Yeah. Number 5, I think. All right. And based on your quiz, my TA is still grading your quiz, the quiz number 6, right? So I don't know your results exactly. He gave me quiz number 5 already. And it should be available in the Blackboard already. So let's analyze this circuit. So first, there is a battery, then resistor, again, multi-loop, then resistor, then another battery, then more resistors. First loop, then second will be here. So again, resistor, another battery. Yeah, that's it. So now let's label EMF 1, EMF 2, EMF 3, R1, R2, R3, R sub 4, and the middle one, R5. Okay, so now let me write down the numbers. Somewhere here. So EMF 1 equals to 3 volts. EMF 2 and 3 the same. Equals to 6. Then R1. Oh, this R1, 2, 3, and 4, they're all the same. Nice. I sound pleasantly surprised, like I didn't pick this problem. But yeah, I usually use it with some problems I change, some problems I recycle from the previous exam review sessions. Right? So. And the final R5, 4 ohms. And again, question is to analyze. Again, analyzing, it means that since we have basically a circuit consists of resistors, again, 3 parameters, Ri, delta V. Resistances are given. Basically, we need to find currents, but once you know currents, then finding potential differences are trivial. Ohm's law, R1, I1, R5, I5, potential differences are a piece of cake. So usually once you found currents, basically you can say that problem is solved. So everything is given, and let's start again with preliminary steps. Right? And as I already told you many times, you have basically freedom to pick any current directions, any travel directions. Basically, it's sort of your universal or constitutional freedom to choose any directions. But the thing is, every semester I take that freedom away from students. Right? And sort of I practice my dictatorship skills. Right? Why? Because when I started teaching this course, I don't know, in 2014, right? And once in the first exam, I gave a problem like this. Students solved, picking all the possible directions. So I assigned my TA to grade this problem. He picked all the exam papers, went to his cubicle. After half an hour, he came back and said, "Kill me." Because can you imagine grading all possible different directions, and he had to sit and check directions the same, directions opposite, right? So it's an insane amount of work, right? Really tedious, right? I realized, oh my God, what I've done, right? So of course I helped him in that semester, and after that I usually give all the directions, and I usually write, don't change those directions, right? Okay, so that's the logic. If I give a problem like this, of course directions will be given, because I care about my TA and our other instructors who are going to grade this problem. Okay, so now once I explained the logic, so now I feel better and I can make those 3 preliminary steps. First of all, we need to identify junction points. So first, junction points. A, B, right? Then, of course, at junction points, currents either merge or split, right? So it means that between junction points, currents must be the same. So we can introduce currents and directions. Right. Currents and directions. So in this branch, from this point A to this point B, a current, for example, I1. Direction, I don't remember. I'll just look at my notes. Okay, this way. That is counterclockwise. So I'm going to use this current. So I1. Then between, again, point A and B, in this part of the circuit, again, current must be the same. Direction, down. I'll just follow my notes. Right, so I2. Then again, now in this branch of the circuit, again, current must be the same. Which direction, clockwise or counterclockwise? Okay, I use this one. It's still counterclockwise. So I3. But of course, in general, as I said, don't sweat. Basically, we are guessing directions, pure guessing. So pick any directions, right, and solve the problem, and then at the end, you will be able to adjust the directions. And the last step, we need to pick travel directions. It's sort of like a preparing ingredients for cooking. So, and then once you start cooking, you just drop ingredients the same pot in the correct order. So travel directions, again, clockwise, counterclockwise, doesn't matter, but you need to pick a direction and stay with that direction. I picked counterclockwise. So loop 1, travel, and here loop 2, again, that's travel direction. Okay, so now steps are done, preliminary steps. And now we can start writing down the actual equations. And writing down the equations, again, once you know the rules, it should take you a few minutes. Top right. Again, rules. If you analyze batteries, you only need to look at the travel directions. If you analyze resistors, you need to look at both travel and current directions. Again, if directions are the same, contribution is negative, right? Minus IR. Directions are opposite, contribution is positive, plus IR. And again, if you don't like those rules, develop your own, as long as they work, right? So you have a freedom. Double E department, guys. If you, for the problems like this, if you are more comfortable working with 2 currents, right? Instead of introducing 3 currents, you can introduce here a current, and there will be sort of overlapping of 2 currents. Go ahead, right? So as long as you can get exactly the same results, of course, the answers must be the same. Use any method you want. But the thing is, I looked through almost all physics books, and they all use 3 current basically methods, right? But in double E departments, you used 2 currents. And when I was a student, also we used 2 current methods. So let's start. First, junction rule. So junction rule. So the total amount of currents, actually, they are here, right? So in must be equal to the total amount of currents out of the junction point. And there are two of them. A. Very trivial. I3 in, I1 out, I2 out. So I3 equals to I1 plus I2. Very banal. Just look at the directions. In, on the right hand, on the left hand side, out, on the right hand side. Oh, flip directions, it doesn't matter. Then, of course, junction point B. You remember every time one of the junction equations are going to be redundant, useless, right? It is not going to give us any useful information, right? It's basically a law. Right? So every time one junction equation is going to be redundant. Like in this case, if we write for B, it will be what? I2 in plus I1. So I1 plus I2 equals to I3. So I1 plus I2 equals to I3, which is obviously exactly the same as the equation number 1. Just move terms, flip the equation. So of course, we don't need this. So equation number 1, we have only one equation. And again, usually, how many equations do we need overall? 3 overall, right? 2 extra equations, because I noticed, like what in the take-home quiz, right? There were so many equations, and then in the in-class quiz, students started writing tons of equations. I remember, right? No, come on. If we have 3 currents, there must be 3 equations. If you have 6 currents, of course, there must be 6 equations in order to solve the problem, right? So, and now a loop rule. Yeah, let me write underneath. So now, loop rule. So let's start with loop number 1. Loop 1. So let's pick a starting point. I usually prefer, as I told you, I have a minor compulsion. I like crossing battery first. I like to see EMF at the beginning of the equation instead of like a tall and slender symbol at the beginning of the equation. Again, minor. So anyway, and so according to the travel direction from this point, first we are going down, or down. It's from plus to minus, so the contribution must be negative. Electric potential is going down, right? It's a rule number 2 which we developed, right? So if you move from plus to minus, contribution is negative minus EMF 1. Again, you just need to remember those rules. Right? And of course, it's good also to know how to justify them if you start doubting yourself, right? For whatever reasons it happens, right? It's normal. So then, after that, and again, when you analyze battery, look at the travel direction only. Don't look at the current direction. I've seen in the past, even good students sometimes were confused. So now, resistor, travel direction this way, current also this way. So both directions are the same. So contribution, negative. Rule number 3, right, about resistor. Directions are the same, minus. So minus current I1, resistor R4. And again, be very careful with subscripts. Because I know I see every semester some unnecessary mistakes, mess with subscripts. Be very careful. So done with this. Now we need to go up. We need to cross this battery. According to travel direction, we're moving up. So from minus to plus, rule number 1, contribution is positive. Plus EMF 2. Plus EMF 2. Right? Again, travel direction is up. So we're moving from the negative electrode to the positive electrode. Potential increases. So plus EMF 2. Okay, so let's keep moving. So now crossing this resistor. Traveling direction still up, but current I2 is down. I feel like you know that Pavlov's dog. Reacting to certain sounds. Okay, I need to, You know what, guys? Let me change the battery immediately because it's getting low. I'm afraid that it will stop recording at in the middle of the problem. Great. So now, traveling direction up, current direction down, contribution must be positive, right? So the last equation, rule number 4, the last rule number 4, contribution is positive, so plus, and again, be careful with subscripts. Now we have current I2. Because again, I told you several times, usually students go through this first part of the circuit, working with I1, 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 and then they move to this resistor and still keep writing I1. No. Now current I2. So be careful, because I can see every semester this really, really unnecessary mistake. So I2, R5. And after that, we need to cross this resistor. Now we're back to current I1 and travel direction that way. Current direction also that way. Directions are the same. Contribution is negative. So minus I1, R1. Minus I1, R1. And so we're back to the starting point. So now we need to complete the equation, right? It is equal to 0. Don't forget to write equals to 0. Because again, that's immediately, it's a mistake, basically. We have to follow the rules of language of mathematics. Right? If it's an equation, it must be equation. So that's equation number 2. And the last one, loop number 2. Wow, I introduced so many elements. So where should I start? Before this point or before that resistor? At this point, which I started where? EMF 3. Okay, so I will start from here. Right. So moving up, travel direction counterclockwise, so we need to cross the battery from minus to plus. Potential increases plus EMF 3. Then resistor, travel direction that way, current also the same way. So directions are the same. Contribution is negative. Minus I3R2. Minus I3 times R2. Then, now we need to go through this connection. So traveling down, current also down. Directions are the same. Again, negative minus I2R5 minus I2R5. Then we need to cross this battery, traveling again down. So from plus to minus, negative contribution. So it will be, potential is going down. So it will be minus EMF2. Minus EMF2. And now we need to go through this resistor. It's the last element in this loop. Travel direction up, current also up, directions the same, contribution again negative, right? So minus I3 R3 minus I sub 3 R3. And equals to 0 because we came back to the starting point. Yeah. Yeah. You can start from any point. Again, I said it's just my minor compulsion. I like to see EMF at the very beginning again. But what's the difference between, for example, if you start from this point or that point? The difference will be in this, okay, in terms of a structure of the equation. What's the difference between, let's say, A plus B plus C equals 0, or let's say B plus A plus C equals 0? It's the same equation, right? So that's pretty much the difference. If you start from a different point, so just the order of the terms are going to be different, but the equation is still the same. Right? Of course, that's why I keep telling you, you can start from any point, you can use any traveling direction, because effectively the equation is going to be the same. But once you pick a certain direction, you need to stay with that direction. You cannot change somewhere in the middle. Right? Yeah, you can use any starting point. So now, if you, let's say, use your calculator or brute force and solve these 3 equations with 3 unknowns, let's say you solve it, and at the end, you will, let's say okay, I calculated. I1 equals to 0.5 amps. So it means what? It means the absolute value of this current I 1.5 volts, and this is the correct direction. So I guessed it right. So I can go and buy a lottery, right? So something like this. It's my lucky day, maybe. So then, I2, let's say I calculated and I ended up with minus 0.25 amps. It means what? The absolute value of this current is 0.25 amps, but my assumption about direction of I2 is wrong. Actual direction of I2 is up. Okay? So I can write, so I2 is actually up. So just make a short statement that about the adjusting direction of the current. Adjusting direction of the current. So this current actually should be up. And the last current, actually again positive. So I3 equals to 0.25 amps. So current is positive. It means that this direction of current I3 is actually correct. In both cases, so if you guessed it right or guessed it wrong, in both cases you'll solve the problem. Yeah. Say it again. No, you don't have to change anything, right? So everything is matched already, right? So you don't have to adjust at the end, except for, yeah, make a statement. So no, you don't have to go back to, all these equations are already satisfied. If you want to resolve one more time the same problem, right, but with the correct directions, again, it's not a crime, but you will waste 15 minutes of your time. Okay, less than that. All right, so fast. Okay. Okay, I will start erasing. And now the next problem about power. So pretty much now what's left, we will discuss power, then RC circuit, and pretty much we can call it a day, right? So it will be around 2.5 hours. Because out of 3 exams, right, probably exam number 2 is, yeah, I would say the easiest. I think it was number 6. I can reduce sensitivity. Sorry. Still. Wow. So, so we have, you know what, let me draw the circuit. So there is a bulb, flashlight bulb, then there is a resistor, and they both in series connected to a battery. And then I will write down what is given and what needs to be found. So let me start with the circuit. So that's my resistor, then bulb, and a battery. Let me label them. So that's R. That's EMF. And okay, now let me write down the numbers. So first, let me start with the bulb, since it's basically is the most important element. The ratings of this bulb is given, wattage. You remember we discussed in the lecture that, bless you, and in the recitation class, and now something. Let's assume that ratings of this bulb okay, let me write like this, like in my notes. So the bulb is rated. Just part of the sentence. The bulb is rated this way. So power is 2 watts. And usually, remember what else is given? The company which builds bulbs assumes that you apply a certain potential difference across that bulb. So let me write. So it's a when what potential difference is 3 volts. So when delta V, let me use subscript B, equals to 3 volts. Flashlight bulb. So it's not just a normal bulb. So 2 watts when delta V equals 3 watts. 3 volts. So then potential difference. So that's information about the bulb, and now potential difference of the battery. So now battery. So EMF equals to 9 volts. Then, yeah, these are numbers. These are numbers. And now what we actually need to find. We need to find the value of this resistor. Okay, let me write that. So we need to find the value of this resistor so that our bulb will be operated with this wattage. So pretty much we want to find the value of this resistor so that potential difference across this bulb will be 3 volts, and as a result, wattage will be 2 watts. So pretty much we just need to adjust our resistor so that the bulb would operate at rated voltage and power. Rated voltage and power. So let me write probably that in sentence. So we need to find R. So that the bulb will operate at rated voltage and power at its rated voltage and power. Because in this case, if we don't adjust R, the value of R, then potential difference across the bulb will be who knows what, and of course, this will not be the actual power of this bulb, right? Okay, so that's what is given. Yeah, everything. So you know what, just before I will start discussing, so of course this will be what? Delta VB, which actually that's what we want. Of course, this will be delta VR. So, and what can you say about the current through both of these? They're actually both resistors, right? Connected in series, and current is going to be the same. So current will be the same. So, and so now, can you actually find the value of this current immediately? Even, for example, without applying, Kirchhoff rules or something like this, look at the wattage of the bulb. Basically, at the end, of course, when we will find the correct value of R, our bulb would operate with these values of delta V, and this will be power dissipated in our bulb. And so if we look, so power, basically, we will know. Current, current is unknown. No, current, delta V is basically we know. Delta V, we know. Power, we know. We should be able to find current flowing through the bulb, right? And we can find that current, and of course, that current will be also flowing through our unknown resistor. So using the rated values of of the bulb, we can find the amount of current that must flow through our bulb. So you can see from these numbers which company provides with the bulb, we can actually immediately calculate the amount of current which is going to flow, right? Okay, so great. So that's the first step. So let me write probably in words. Okay, since we want to operate the bulb at the rated values, at the rated values, right? So we can calculate current. We can get current. And we're going to use the first formula, P equals I delta V. Again, it depends on what is given. This can be more convenient, that or that can be more convenient. In this case, the first one is the most convenient. So power, you know what? Let me put here, add subscript. It makes sense, right? So PB, then delta VB. B stands for bulb. It makes sense. So P sub B equals to I and delta V sub B. Again, current, I'm not adding any subscripts because current is going to be the same for both elements. So, great. So as a result, current will be equal to the power of the bulb divided by the potential difference across the bulb. Okay, I'm not going to calculate, although you can easily calculate actually a number. But I will just drag the symbols. And you know what, let me frame with green because it's sort of essential preliminary result. Okay, so now, let's try to now apply. So yeah, what we have to find? R. We need to find R. Let's try to use Kirchhoff rules in order to combine all these elements in one equation, hoping that it might help. Because plus we know the current, so we will know the EMF is given, right? So potential difference across the bulb we will know, and potential difference across the resistor will be just I, which we calculated I times unknown R. So pretty much if we apply Kirchhoff rules, it will be one equation with one unknown R immediately, right? So it looks like Kirchhoff rule, loop rule, is going to help us to actually solve the problem, right? Okay, so now let me write it down. So let's apply loop rule. So potential difference across, wait, you didn't see this? Delta VI equals to 0. And to be precise, let's, like in the previous problem, let me introduce also travel direction. Right, so which one I picked? I picked this way. So that's travel direction. This case, it's a clockwise. It doesn't matter which direction you pick, but in this case, I pick clockwise. Right. So, a battery from minus to plus, rule number 1, contribution is positive, plus EMF. Then, resistor, unknown resistor R, direction, travel direction this way. Current, obviously, right, so we don't have to guess the current direction. There's only one battery from plus to minus. So direction of the current, we know. So travel and current directions are the same, so it will be minus I times R. Again, our R is unknown right now. We're still in the search. All right, and then potential difference across the bulb we know because we want to operate at the rated value, so we want to get delta V. So minus, and of course, voltage drop. Voltage drop, again, is basically a resistor, right? Current that way, travel direction that way, so of course, it will be negative minus, but of course, now we know absolute value. So we don't write minus IR, we write minus delta V. And we're back to the starting point, so equals to 0. One equation, one unknown, right? So unknown is R. The rest are given. This is given. This we just found, I. And delta V was given again from the very beginning. Right? So now let's solve it for R. Okay, let me do it step by step. So EMF minus delta V sub B equals to I times R. I will go to the other side, to the denominator, right? So it will be R equals to EMF minus delta VB divided by current. And current we know. Again, you could have calculated, but I prefer to insert it in our expression. Use that expression. So it's a P divided by delta V. Again, this is my explanation box, basically. Oh no, now it's leaving. GoPro is still dragging its feet with my laptop. Draining my laptop. All right. Yeah. So now I just need to plug it. So EMF minus delta VB divided by power divided by delta VB. Okay, that delta VB will go upstairs in the numerator. I just want to get the expression, basically delta VB and ratio of EMF minus potential difference across the bulb divided by the power of the bulb. Let me check if I got the same as in my notes. Yeah, it would be difficult to get lost somewhere. Right, okay, so now let's plug numbers. Since we managed to get almost to the end, so now let's enjoy plugging numbers. So R delta V 3 volts, then what's the battery? 9 volts minus 3 volts and divided by power 2 watts. So this will be 6 over 2, 3. 3 times 3, 9 ohms. So that should be the value of the resistor. In order to operate our bulb at the rated values of what company provides. So they expect that light bulb, okay, flashlight bulb should operate at 3 volts. And in this case, it will generate 2 watts of power. Actually, yeah, problem is solved. But let me ask you an additional question. What if I want, for example, I know, just for fun, I want to find also resistance of the bulb. Can we find resistance of the bulb? Which way? Yeah, again, so basically, again, since it operated at the rated value, so we know power, delta V is also given. So we can find resistance like we did in the clicker question during the lecture. So it's exactly the same story. And in this case, resistance of the bulb is basically truly intrinsic parameter of the bulb. It doesn't matter where you take that bulb, resistance is going to be the same. Right? Power, of course, change. You can apply different potential difference. It depends on your circuit. But the resistance is going to be the same. So let me also add. Right, so additional question. So resistance. Let me erase this. So resistance of the bulb will be equal to the power of the bulb divided by where is it? Wait, not the power. Delta V. You know what? Let me write first the formula for the power. P of the bulb equals to delta V squared divided by R, and of course from here, less confusing will be for everyone. So RB equals to delta V sub B squared divided by the power. If you plug numbers, 3 squared divided by 2, it's a 4.5 ohms. Okay, done. So, of course, if everything works fine in terms of footage, right, and audio, probably somewhere around Sunday, I will upload the video to YouTube. So you can, if you want, you can review it. Right? And of course, I will send you my slides. I'm not slides, damn it. Notes, PDF file. So probably the last problem. So it's been 2 hours, so probably another 20 minutes would be last. So RC circuit, and I want to discuss charging situation. But again, it's basically discharging, charging. In terms of complexity, they're similar, but again, guys, be careful. If it's a charging case, don't use the functions for a discharging situation. I've seen this in the past. It's really, really kind of silly, right? Making that type of mistakes. Right? And again, usually in the formula sheet, I write so charging and a bunch of functions. Then discharging. Okay. Okay. So now I got your approval. So now I can start erasing. And it's 7. When you present something, lecture, time flies really fast. You realize it's already 15 minutes has passed. So RC circuit, and as I said, it's a charging case. Yeah, we're going to charge a capacitor. Charging capacitor. Yeah, I will first draw a circuit, and then I will start writing down numbers. It makes sense. It makes more sense. So let's say we have battery. Then, yeah, of course, we assume that there is a switch. And then 2 resistors, R1 and 2. And then there are 2 capacitors. This. And let's say one will be here. You know what, I don't like it's in the sort of to the side. Let me put it somewhere in the middle, closer to the middle. So R1, R2. Okay, so first this is EMF, then R1, R2, then C1 and C2. And actually, resistors are the same. Capacitors are also the same. So let's say that R1 equals to R2 equals to 2.2 kilo ohms. And C1 equals to C2 equals to 3.8 microfarads. And of course, EMF is given 12 volts. So these are numbers. And now the question. We need to find the moment of time when the value of the current is going to reach a certain, when the current is going to reach a certain value, right? And that is 1.5 milliamps. So let me write it down. So we need to find, it's somewhat similar to the question, to the problem which we discussed in the recitation class, but I increase complexity slightly of the system. So we need to find, let's call it T1, moment of time, because what happens, guys? First, capacitors are empty, right? And first, at the initial moment of time, there will be very large current, the highest possible. Again, we even watch the movie, right? And then current decays. So pretty much we just need to find the moment of time when current is going to reach 1.5 milliamps. Right? So, and we don't know the maximum amount of current. We will have to find actually. So we need to find T1 when I1, it's basically current at that moment of time, equals to 1.5 milliamps. And you know what? Let me also show it on the picture, on a graph. If I plot current versus time, so let's say this is our current. Let's say this is time. Of course, it decays. So let's say this is I naught, and then it decays like this. And this is I naught. This is the maximum current, which we still don't know. But I just want to show what we want to find. We want to find some moment of time T1. It's our question. When current is going to have the value of I1, which is 1.5 milliamps. Basically, that's what we need to find. Yeah. Because we know? No, we discussed, right? So look, like in simple language, like I was explaining to you, right? So in the lecture, you remember it? So first, all these electrons sitting over there, crowded, right? So they're hitting each other. You remember, like charges repel, right? And once you close the switch, they see basically like a bright light at the end of the tunnel, right? Empty capacitors, and of course they will start running like crazy towards that, right? Because they want to get rid of each other. But so at the initial moment of time, there must be very, very large current. Lots of charges want to go there. But once they arrive to the capacitors, what are those electrons which are already settled down in the capacitor? What are they going to do to the new coming electrons? They're going to repel them, right? So it will be more and more difficult for new electrons to arrive into the capacitor, right? So it's in simple words. So of course, as a result, current is going to decay. In terms of language, in terms of physics, right? So look, first, potential difference across the capacitor is 0. And here, potential difference across the battery is EMF, right? So right now, there will be very large potential difference, and that large potential difference is going to create a very large amount of current, right? Actually, I will talk about that when we will have to find I naught, right? So I will talk about that at that moment. Because capacitors are going to be empty, so the voltage drop across the capacitors are going to be 0. So the whole voltage drop, all this EMF, is going to be across these two resistors, giving us the largest potential difference across the resistors, giving us the largest amount of current. Then, once potential difference across capacitor starts appearing, so potential difference across the resistor starts getting smaller, and of course, as a result, current is going to be smaller. So EMF divided by R1 plus R2, and current is going to get smaller and smaller and smaller. Okay, so now, so at the end, of course, we will have to just grab the function which describes how current changes. Plus, you ask, so how do we know that current behaves like this? Actually, it's this because we're discussing this charging case. We derived this. Actually, we derived this, but then you can just differentiate that and you can get that. So basically, we derived this. Right? Again, applying Kirchhoff loop rule and then integrated that differential equation. And that was mathematically derived. Okay, so that's the function which describes how current changes. So of course, we will have to use it at some point sooner or later. But now, in order to understand what needs to be found, I want to write this down. E naught and e to the power of minus t over tau. Of course, we will have to find, you have to apply that for the moment of time t1. So this will be I1. And we will have to find that T1. But before we start applying that and start searching for T1, what else must be found? We need to make two preliminary steps before we can start applying, actually, using this function. First, we need to find time constant, right? That will be the first preliminary step. And then second, we will have to find this maximum amount of current, Once we find tau and I naught, then we will have to go back to this function, apply the moment of time T1, and solve it for T1. But first, we need to find tau and I naught. So first, we need to find I naught and tau. Let's start with tau. It's probably the easiest. So the difference between this circuit and circuits which we use to derive these functions, here we had one resistor, one capacitor. Now we have two resistors, two capacitors. But we know the equivalent stuff, right? Equivalent resistors and equivalent capacitors. Right? So we can apply that. So these two resistors obviously connected in series, right? And two capacitors are also connected in series. All of them are connected in series, right? So this also in series. So we can find C equivalent and R equivalent. So I will start with R equivalent because it's easier. So it's R1 plus R2. Right? So it will be R1 plus R2. I'm not going to plug numbers. I will just drag in symbols. Then C equivalent, so in series, so I have to use reciprocal. So I need to use this 1 over C, 1 over C. Right, so it's a 1 over C equivalent equals to 1 over C1 plus 1 over C2. So again, if you bring to the common denominator and then flip it, you will get C equivalent equals to the product of C1 and C2 divided by the sum of C1 and C2. And so now, of course, we can multiply them to find the actual RC time constant for this more complicated circuit. So let me put this like this and write. So tau equals to R equivalent, C equivalent. Again, if you calculate number, it's great. No, it does help. My laptop works. So it will be R1 plus R2 and C1, C2 divided by C1 plus C2. So that's our RC time constant. Now, current, maximum current. Like so sensitive. So now it's actually about your question. So how can we find maximum current? So at maximum current is at the initial moment of time when potential difference, again, as I said a few minutes ago, potential difference across this is 0. It's empty. Potential difference across this also 0 because it's empty. So all this EMF is going to be across these two resistors. So it will be EMF divided by the equivalent resistance, basically R1 plus R2. That will be the maximum amount of current. Okay, so now let me write what I have in my notes. At t equals 0, let me write this. C equivalent is empty because, again, electrons haven't reached it yet. They just started running. And, of course, delta V across our resistors equals to the EMF, which is the potential difference across our ideal battery EMF, right? So, and now Ohm's law, EMF equals IR, but we need to find okay, I know it's a maximum, right? So I can write that I sub 0 equals to EMF divided by R1 plus R2. Okay, so these are preliminary results. And now after finding tau, you know what, probably I should frame them with a little bit so easier for me would be to find them. And now back to our equation. You know, I think I should be able to move to this side of the whiteboard. Camera is still in the field of view of camera still. So, and now back to this. back to our function. So I at T1, which we actually know, okay, I label it as I1, right? We know that, equals to I naught, which we just found, and e to the power of minus T1 divided by tau. Only one unknown, T1. That's what we need to find, right? The rest was either given or we found, right? So that's our unknown. Okay, in our recitation class, we solved almost very, very similar equation. So I naught goes to this side. Okay, let me do simple manipulations, mathematical. Of course, at this point, you know what to do next, right? You need to take natural log of both sides in order to drop that power where our unknown is, right? So natural log of I1 over I naught equals to natural log of e to the power of minus T1 over tau. Okay, so natural log of the ratio of these currents equals to minus T1 over tau. Now just pretty much algebra, moving terms around. So T1 equals to minus tau and natural log of the ratio. And like in my recitation classes, I told you, whenever there is a minus in front of everything, I usually try to hide it somewhere, following the suggestions of psychologists, right? Be positive. And you remember that basically log properties of log functions. So if you have a natural log of, let's say, x to the power of minus 1, it's a minus natural log of x. And that's what we have. We have minus in front. So we can just basically move it over here to the power of I1 over I naught to the power of minus 1. You remember that? Natural log properties. Okay, so that's what I'm planning to use. So it will be T1 equals to tau natural log of I1 over I naught to the power of minus 1. And so we just need to flip that ratio. So it's a tau natural log of I naught over I1. So that's the answer, but we need to plug the numbers. I will just plug these expressions, right? So in order to have impressive, complicated structure. So T1 equals, so tau, it's this, yeah. Right. R1 plus R2, then C1, C2 divided by C1 plus C2. So that's our tau. Right. And natural log of this ratio. Right. So where is my I naught? It's that. So EMF divided by R1 plus R2 and times I1. Yeah. Okay, so that's the expression. Final expression for the moment of time when current is going to reach this value of I1. But let me check to make sure that everything is correct. No, yeah, obviously. Okay, so if you plug numbers, all right, so which of course I'm not going to do, so you will get 5.0 times 10 to the power of minus 3 seconds. 5 milliseconds. Reached the final result and hasn't framed it. Strange. Again, problems are about RC circuits. Usually there are two types of them, right? So let's say moment of time is given, you need to find the value of current or charge or potential. Or the value of something is given at a certain, and you need to find at which moment of time that happens. And of course, there might be some preliminary steps, like in this case, you need to find first time constant, or maybe a maximum potential difference or maximum current at the initial moment of time. Something like this. So again, usually students do reasonably well with the problems of this type. Okay, so there are some additional sort of almost conceptual questions, but again, it's a finding RC circuit. For example, if you have, I don't know, two resistors, first in parallel, then in series, or capacitors in parallel, it's basically, again, applying those formulas a few more times. Nothing new. So that's what I prepared for you. So it's like 2 hours, 20 minutes. 7 problems. It should be enough.